Greetings to everyone. This work regards a multi-objective optimization approach for planning the urban shift to electromobility considering financial, environmental, and infrastructural elements. The work has been performed by myself, Dr. Philippos Algianakis, and Professor Lukas Dimitriou, who is also the director of our lab, namely the Lab for Transport Engineering of the University of Electromobility can be regarded as the future of urban transport and a major shift to vehicles' consumer behavior, and is a promising improvement to urban environment and a better standard of living with lower noise levels and emissions. However, sustainability is a totally different issue, and it depends on the urban system it is applied to. For our case, the electromobility system is itself a complicated system combining both transport and energy sectors. To optimally plan sustainability policies, different aspects of sustainability need to be considered under an appropriate assessment tool assessing a wide time frame, which for our case is about 30 years. During this time frame, a time-dependent complex system is formed, which has to be solved to obtain policy outcomes and steps that should be taken to obtain the sustainability targets. The framework provided herein performs a multi-objective optimization for pairs of system sectors and sustainability aspects. Now, the main parts of the framework consist of the system, which is analytically defined, the sensitivity analysis performed to reduce the complexity of the system, the multi-objective particle swarm optimization performed to obtain solutions for all possible pairs of sectors and sustainability outcomes, and the actual policy outcomes for planning the electromobility for the case of Cyprus. This slide gives a snapshot of the electromobility system for the case of Nicosia. The system is presented using a spaghetti diagram, as we can see here, where directed arrows represent relationships and correspond to certain equations, which we can see on the right-hand side. Two main colors in the central area show the two main sectors of the transport sector and the energy sector of the electromobility system. If we move to the outer left and right parts, we can see the policies affecting each sector and the overall system. For the system's sustainability assessment, the cost-benefit analysis is used, generating the benefits and costs to the upper and lower sides of the diagram. The initial system, as was seen, is highly complex, composed of 183 time-dependent variables governed by 64 equations that correspond only for 1 year of the 30-year time frame. Moreover, the system is composed of 9 sustainability outcomes whose pairs need to be solved. A brief explanation of what these outcomes regard is presented on the table that shows our system divided into sectors and to sustainability aspects. The complexity of the system was reduced using sensitivity analysis to provide linear equations for each sustainability outcome that would be used. They are organized in pairs of all possible sustainability and sector combinations, which in total are 36. Its subplot shows the convergence diagram of each pair optimized. As can be seen, in many cases, contradicting sustainability pairs form Pareto optimal solutions, while single solutions exist when contradicting criteria do not. So, among the subplots, a certain pair was selected to show the policy outcomes generated, which is this one that we're going to see on the next slide. Here we can have a closer look at the selected solution, set of solutions. So at the left diagram, the Pareto optimal solutions are presented to select policies that optimize socio-environmental aspect of transport and the overall aspect of the system. Solutions are analytically presented in the next 3 plots, indicating the values for taxation policy variables, energy variables, and incentive policies. Each line represents one policy solution divided in 5-year interval policies, colored based on the color maps shown in each figures next to each figure. Now, as can be seen, there is diversification among the solutions provided for all the different solutions. Moving to our conclusions, this work presented a framework under which electromobility could be optimally planned. The framework was composed of a systems approach, sustainability assessment tools, sensitivity analysis, and multi-objective optimization. The framework was showcased for Cyprus's capital Nicosia, the results of which showed that the framework provides an exploratory tool for the sustainability assessment, as well as a policy planning tool for the electromobility adoption system. Contradicting pairs indicate where decision makers should focus. The framework also provides specific policy solutions to obtain certain sustainability targets for the desired pair of sustainability. Moreover, decision makers are provided with more flexible assistance to design policies that better satisfy society's